We can start. Welcome everyone on our next session. As you could see from our announcement, unfortunately, one of our speakers got sick and they are not able to present, but you can find some materials for their session in the event chat. But we are happy that we find the great replacement for this talk, and I would like to welcome Daniel Walsh, who will tell us something about the containers in the cars. So then, stage
okay.
is yours.
Yeah, thanks. By the way, I found out about this. I was given this talk about 2 hours ago, so I have no slides prepared, but we'll talk off the cuff and we'll see what we get through. About 6-7 months ago, I switched groups inside of Red Hat. I went from chief architect on the container engines team to working on what's called RHEL for Edge, Red Hat Enterprise Linux for Edge, and specifically into a group called Containers on Wheels. So Red Hat has a large effort to sort of investigate what it would take to get the base operating system into automobiles going forward. I continue to work with containers closely, and I'm really looking at moving things like Podman and other tools into vehicles. Let's start talking about a couple of things. So what's going on in the OEM world of automobiles right now is there's been a lot of effort to quote get Kubernetes in a car. And the basic idea was to, a lot of the car companies and the OEMs for the car companies want to basically innovate quicker. They see what Tesla has been doing as far as innovation, and they want to, take advantage of more of cloud native type development. And sometimes they ask for, as I said, they quote this as Kubernetes in a car. Well, back in October, myself and a couple of my colleagues, Alex Larson and Pierre Chaban, wrote an article basically explaining why you really don't want Kubernetes in a car, but you want sort of the cloud native effect. The problem with Kubernetes is in a car is twofold. One is Kubernetes has basically defines software as eventually it'll get to the state that you want. Whereas in a car, we want to know that the state is instantaneously moved to. So for example, imagine you're driving your car, you sit down, you start your car, you want certain services up and running in the car. You put the car into reverse, you need the backup camera started, you need signals going off, you need sensors to find out if people are around, and that can't eventually happen. That has to happen instantly. In car and a lot of other edge type devices, they have what's called functional safety. So functional safety basically means that we have to make sure, do everything in our power to make sure that the machine that we're putting these computers in is functionally safe and that won't hurt anybody. And so these requirements mean that something that eventually gets to the state of consistency like Kubernetes would not work. The other problem with Kubernetes is that there's a decent amount of overhead on it that we really don't want to have to pay for in a car. And finally, in the car, there's not going to be virtual machines coming and going. There's not going to be cloud instances coming and going. It's really a sort of a static environment where you have probably, say, 1 to 4 computers in the car, and we want to get coordination between them. So if you read this article, we go heavily into describing how we plan on, we talk about how we get to this, Kubernetes type environment without actually using Kubernetes. The next thing, one of the tools, so when we're running in a car, we want to, again, think of states. So when you're in a car, you want to move from state to state, not as in the United States, but more of, you're in parking mode, you're in reverse mode, you're in forward mode with something like self-driving, and then you need to, different modes. And so we looked at how we would do this, and a lot of these states follow sort of the system D mode. So if you think about booting up a system, your computer system, you move from boot up mode to multi-user mode, and then to say graphical user mode. In each one of these modes, system D is starting and stopping different services on the system. So as you transition from mode to mode, so we looked at that as being a good analogy of what you're doing when you're riding a car. But we needed these. So what we're looking at building inside of the car is basically using system D as the main manager of services on each one of the computer systems. So again, backup mode might be a set of services, and those services might be containerized. And then we're able to shift from different modes to different modes. But we needed to relay system D services amongst multiple nodes. We've invented a tool called Herter, and Herter is the German word for shepherd. So we want to shepherd the processes up and down in the states around the system. So what Herter is a multi-node system D service controller that we've developed for coordinating different services among multiple computers inside of the car. So it's since we're relying on system D orchestration, we want applications to be can be containerized, but don't have to be. And we want, since system D integrates so well with Podman, we've actually invented a new thing that was talked about yesterday. I think it's Scott's talk about a thing called Quadlet, and I'll show you an example of that later on in this session. So we also want to have multi-node support, and again, it's limited nodes, and the nodes do not come and go. So really, we're looking at these services as being sort of hard-coded or static in the environment, although we are looking at potentially eventually allowing some variability on the nodes. And then we're looking at using the API to talk to system D, and the API to pass around the environment is going to be D-bus based. So the way you talk to system D right now, even using system control and tools like that, is it talks to D-bus API. So when we looked at Herter, all we wanted to do was relay the D-bus API across multiple nodes. So the architecture of Herter comes down to three different tools, fairly simple. There's a Herter daemon on a single main node. So this is going to be controlled by a main node. And this is the application controlling system D service. And it runs primarily on a single node. And this is where a controlling application developed by, say, a third party, usually the automobile companies, would communicate. But this is the tool that's going to relay communication between the nodes. And Herter, the daemon, talks to Herter agents, and there'll be one agent on each one of the nodes. And these agents will receive notification from Herter, and they will also communicate back information. So the Herter agents are listening to system D and communicating with system D and over D-bus. And basically what's happening here is, say a service shuts down, that will go to the Herter agent, and the Herter agent then will relay it back to the main Herter manager, and then Herter manager, if an agent is asking Herter manager will relay that message back to it. Finally, there's a tool called Herter Control, and Herter Control is really just a CLI that talks to Herter. And it really is for human beings. So if you want to go in and just work with the system and see how it works and play around with it, Herter Control is a tool for doing that. And also we use it for debugging purposes and running in CI/CD systems. In the car, we would envision almost never having to use Herter Control. There would be, again, a third-party application or a vendor's application that would be communicating with the Herter daemon. So here gives you a global overview of what Herter looks like. So the OEM tool from the manufacturer is talking D-bus daemon to Herter, and Herter then goes out to talk to either a locally running agent on the system, and that local agent is monitoring or manipulating system D, and system D manages services. Similarly, a Herter on remote machines will be talking to Herter agents over IP. To the agents, and then each one of those agents would again be talking to system D. So I think that's all I really want to cover with Herter at this point. But you can go in and examine the Herter project, which is on GitHub containers /Herter. And it's under heavy development. We just went to .0.1.0 was just released this week. There's lots of additional development going on in it, and we're still figuring out how we're going to set up security communication between the nodes. Things like that hasn't been completed yet, but it's at a state right now where you can actually play with it. So we talked about running services, systemd services to run all the applications that you're going to be running inside of your car. We also, to get more of the cloud native, though, we needed to have an OCI engine for running, basically OCI containers and to get you the cloud native feel. And what we looked at for doing that is obviously Podman. One of the key nice things about Podman is that when you're running under a systemd service, Podman goes away. So when an application gets configured and started, the Podman executable is no longer running, as opposed to, say, something like the Docker daemon or even in the Kubernetes world. So in Kubernetes world, you're always running the entire Kubernetes infrastructure when the applications are running. But in the case of systemd-based containerized system, we're just running Podman to configure or to shut down the service. So it's Podman is really just running while it's changing the configuration of the system. But we had when the automotive team started looking at Podman had some fundamental problems from the automobile's point of view. The number one goal of again, changing states is that these states changes have to be happening at almost instantaneous time. So we noticed that something that the car team, the container on wheels team, basically came in with the requirement that Podman had to start containers as fast as possible. So this is, so when we first started examining the time that it took to start a container on a slow under ARM type box, basically Raspberry Pis, we were seeing up to 1.9 seconds to actually get to the point where the container is starting on underneath a real-time kernel. And so the automobile engineers started to look at how we could speed up the time Podman could start. The OEMs were asking us to start it up in basically as fast as possible. Matter of fact, they often joked that they needed to start a container in negative time. So there was a large effort to go on to figure out why Podman takes so long to start a container on a underutilized system. Again, on my laptop, I always felt like, it takes a half second. So for a human being to wait for a container to start in a half second, that's not a problem. In the Kubernetes world, that's never been a problem. But when you get to, sort of an edge device that has to instantaneously change, it becomes a big problem. So we went through and examined up and down the stack where time was being spent on starting a container, and we found a lot of sort of low-hanging fruit. There was actually different, not bad coding practices, but some coding practices that could be improved in order to enhance the speed. So we very quickly were able to speed it up to starting a container in a second. And most of these changes happened in crun and in Podman. crun was doing some re-execing stuff, loading seccomp. We were always compiling the seccomp filter as there was, we could pre-compile them. There's other, Podman and Golang had, every time you use a regex, it actually compiles the regex at start time as opposed to when you need it. So by moving some of the regex compilations to only when necessary, actually helps speed up. And then we're also, because we were using real-time kernel, we found some issues in the real-time kernel that we actually had opened up requests to the real-time kernel to fix some heavy overhead that was actually slowing down Podman. The next thing we looked at is how could we speed up Podman by one of the things that the car we've decided with Podman in the car was that we really did not want containers to persist after reboot. So basically, when you shut down a service, the container is destroyed, and each time you start a container, it is created afresh. This meant that we really had no data that had to be stored on the file system for the containers, and Podman use of container storage does a lot of syncing and a lot of reads and writes to physical file storage on disk. So we added a feature to container storage, and that was moved into Podman called Transient Store, which instead of storing storage on top of the file system, we started to store a lot of the data on top of temp FSs. And this, again, sped up container processing, where we started to, as you scroll down the screen, you'll see that some of the times here start to drop down to a half second and even less. And so finally, we were able to get down to, you see in this box with all of the things turned on and all the features in, we've moved from almost 2 seconds down to a little under 0.3 seconds. So we've had a 6-time speed up in the ability for Podman to start up a container just by going through this work. We've continued to look for stuff, but obviously as you get down to smaller and smaller times, the amount of speed up that we're able to get is still overhead. But if you're running containers on a edge device and you don't want the containers to persist, you might want to look into how we went around about this process and how we configure Podman. We do plan on writing a blog that describes exactly how to run Podman as quick as possible, or again, for edge type devices at startup time. So that's the second thing we worked on for automobiles. Now, the third thing that I've been working on is called QM, or quality management. In a car, it tends, on the computer systems, you tend to be running two different types of applications. So you can imagine if you're running a self-driving car, that certain applications have to run one way, and then you have sort of the infotainment system and applications that are less important to the safety of a car run in the same. We want to be able to run them on the same platform. And in the car world, those are divided into two categories. So there's what I call functional safety, again, things that are involved in maintaining the safety of the vehicle. In the car world, those are called ASIL-B. And the other applications that run on your computers for, say, infotainment type applications are called QM, or quality management. And what we needed to do in the car world is implement something called freedom from interference. So the basic idea of freedom from interference is to make sure that a application that's running in the QM environment, the quality management environment, doesn't interfere with applications running in the functional safety. So the analogy I use, which is kind of a shaky analogy, but imagine you're driving your car and you say, I want to load Spotify. So Spotify communicates with System D. System D launches Podman, and then Spotify comes up and running. If simultaneously with the human being triggering that event, someone steps off of a curb, and the application, the functional safety of the self-driving car has to launch the braking application, it would talk to System D. System D would talk to Podman, and then the braking application would launch. So by doing that, we need to make sure that the launching of the Spotify application does not interfere with the launching of the braking application. So not only do we need to run each one of the containers in an isolated environment, we're looking at using something like C groups to maintain that functional safety, but we also need to make sure that the entire tooling used to launch applications would not do that. So quickly, I've set up a tooling here to be able to do that. One of the first things I did is I wrote SE Linux policy for controlling what the QM environment did. So we run the entire QM environment on the host. in an isolated area. We wanted to run systemd in it, and I will show you quickly. There's a quick install script here that is going to set up a rootfs directory. So on this particular directory on disk, basically use a libqm rootfs, we're going to install software that's going to be used to run systemd in this environment. And here we see inside of my install script, I'm actually installing a few applications here. I'm installing Podman and systemd because we're probably going to be running containers in this QM environment. And I install SE Linux policy because I want to have SE Linux separation. I also install DNF just so I can update it, and IPutils to get ping. The rest of this environment is just this command is just installing SE Linux in the environment to again allow us to set up this isolated environment to make sure it doesn't break. And then I'm also moving this containers.conf into the rootfs environment. So this is into the separated environment, and I'll show you that containers.conf in a second. This next section of the install script is actually modifying SE Linux to make sure the file labeling happens correctly in the environment. And that's all that's happening. So we're installing, well, finally, I'm doing this QM container, which is actually a quadlet. So let me step back, and I will show you the quadlet that I'm used to configure this type of environment. So we're going to start down here. So a quadlet is like a systemd unit file that basically embeds, it generates a podman command to run well under a systemd unit file. But it has a fairly simple syntax. And if you're familiar with systemd tooling, you can get it should be fairly quick to learn how to run containers underneath systemd. So this container section of the systemd unit file describes what's going to happen in this environment. Down here, you'll notice that we're not using an OCI image to do this, but we're actually running a containerized environment directly off of the rootfs directly off that directory I installed. And up here, we're showing that we're running init. So we're going to be running systemd inside of this QM environment. We're naming it QM. We're actually passing in all capabilities. Since we're going to be running Podman inside this environment, we need to have a fairly privileged containerized environment. We're sharing the host with the network underneath it. This flag right here tells the containerized environment to run SE Linux inside of the containerized environment. So I'm running SE Linux in both on the host and for container separation, so I can run Podman inside of the containerized environment. Finally, you see here the SE Linux labels being passed in. So I'm running all the containerized processes other than the containers are going to run as QMT and QM file T. So I'm running them all with an isolated environment. The top section here shows you what we're really after here, which is to make sure that this QM environment doesn't interfere with the rest of the host. So these are systemd settings that can be set on the environment to guarantee me isolation. So for example, this setting here tells systemd to run all QM processes and any QM containers on basically specifically on nodes 6 to 11. CPU white says that if the system is under CPU pressure, then QM processes get 50% of all, on average, all system calls. I mean, all processes get 100. We're basically saying we'll take half as many as a normal process on the system to cut our weight in half. This is for disks, similar to that. The rest of these fields are all about telling the killer to kill us first, to pick us to be killed first. And you can see some of that here. It's basically all about saying to killer to kill us. So quickly, I'm going to show you what this environment looks like. So if I do status QM, you see that the status is not running. If I just do a status start QM, now I have a QM running. You'll notice that this is running in a separate slice. So this is all those rules are applied to the slice. And inside of this containerized environment, you see only and it is running. Only systemd is running in the environment. So now if I can do a podman exec TIQM shell. This is why you don't do these at last second. slice. Okay, so you see I'm inside of the environment now. I'm running as a QM process on the system, and I can start to run containers in this environment. So this environment is totally isolated from the host. We're running under all those C groups constraints. And basically, I can run an entire stack of Podman inside of this environment that is isolated from Podman on the host, but yet still on the host system and still in the ASL environment. I can see what's going on inside of the containers. And I know I'm running out of time, and I want to open up to some questions. So I will stop at this point sharing and see if anybody has any questions. Sorry about that being rushed, but anybody have any questions?
I don't see any in the Q&A section, neither in the chat. Michael is writing that was cool. So you were not rushing; it was understandable.
So the QM package is currently being we're looking at packaging it and making it available in Fedora, so other people can start to play around with this. I don't think that I think this environment is could be potentially useful for other people who want to build sort of isolated environments inside of their vehicle and isolated from the host. We're not, while this is all being done for automotive, there is potentially lots of other functionally safe type environments. Think large machinery, aircraft, other environments. And so this is something that, again, we're experimenting with, and we're actually learning how to deal with this stuff. So, so let's see. What is the relationship between QM and Herta? So Herta is all about managing systemds. So if you think about, if you had 4 computers in your car, and you had each one of those computers was running a QM environment, you would actually have 8 systemds running. So Herta will have an agent running in each one of the systemds, even underneath QM, so that the Herta would be able to relay information like, your Spotify application crashed, and that would go back to the controller to tell it what's going on. The controller also can do things like, okay, trigger an event. The user just pressed on the GUI to start the Spotify app, and would go down to the QM that is running Spotify and tell it to do it. So the Herta would be almost like additional nodes. We don't do this with VMs because of the overhead and the lack of visibility from the ASL into what's going on in the QM environment. So we want to allow things like killers and specialized tools to kill and start and stop processes inside of the QM environment.
Thank you, Dan. As people are saying, this talk could be even for more hours, but we don't have that time.
I'll be doing an extended version of this with actual slides at DEF CONF. So if you're showing up the DEF CONF check, I'll be covering it at that point.
Very nice. Very nice. DEF CONF is in June 16, I think. Yeah. So check that out. Thank you so much, Dan.
And attached at the top of the chat, you can see a lot of the information. All the links are there, and also you can read my book. You can get links to my book, and my book is fully available for free if you want, or if you want to put $2 in my pocket, you can actually buy it. So,
very nice. Thank you, Dan, and thank you for stepping up for the replacement for the other talk. Much appreciated. And thanks for joining, everyone. Hope you join us for the next session. See you around.